Welcome back. Now let's take the third scenario where we extend the state diagram in the previous case by changing the condition of transition. Fine. Such that, so now the new condition, the condition on the transition from state off to state, the first on state, which we had named on one. Fine. And the new condition is that it requires, earlier we used to have only clock. So every time a positive edge of the clock happened, there was a transition from off to on one state. But this time round, in the next case, we will consider a condition where we don't only require the rising clock, but also an external input, let's call it B, should be 1. Fine. And if B is not 1, so we also add a transition in case B is not 0 from off back to off when B is equivalent to 0. Fine. In the second example, we had considered one off state and three on states, off, on one, on two, on three, but the condition of transition from one state to next state was purely based on the clock. Now I'm introducing an additional thing wherein the first transition, that is from off state to on one state, apart from depending on the positive edge of the clock, it also depends upon the external input, which you are calling B. That should be high. So let's first draw the timing diagram. This is how we have been approaching. So let's draw the timing diagram first. So again, I will have a clock signal here. Quickly, I will draw the clock. One period, second one, third, fourth, fifth, sixth, and so on. Fine. And as usual, we are interested in the positive edges, means these edges we are interested in. So let's drop here projections so that we can keep a track of these edges. Fine, so this is my clock. But this time round, I also have an external input B. This is a new thing. So external input B, say it remains low for some time, then suddenly, let's say here, it goes high for some time, then it drops to 0 again. Fine, let this be the external input B. Fine. Now see, it is the value on the B and then the clock that will determine currently what is the behavior of my circuit. Fine, so as far as plotting the state goes, B is 0, so let me just first draw these states. So B is 0, that means my initial state off. Now, if I have to move from off state to on one, it requires a rising clock edge that is there, but it also requires B should be equivalent to 1. But for the time being, B is 0, so I will continue to remain in the off state. Third clock cycle, again off state. Now fourth clock cycle, again off state. And it's only at this clock cycle where my B goes high. So B goes high, clock goes high. Now I will move to on 1. Fine. Then thereafter from on 1 to on 2 and the other states, we don't need any value of B. So once we have reached on 1, another pause stage comes, we move to on 2, then on 3 and so on. Fine. And as for X, so this is basically the state. And as far as the output goes, off state 0, 0, 0, 0, then it goes 1, 1, 1. So this is the timing behavior. And if I have to capture the finite state machine for this case, again, I will have a set of states. I will have 4 states: off, on 1, on 2, on 3. So this is off, on 1, on 2, on 3. Again, let this be my initial state. Fine. And again, in each state, there will be some output. Off state x is equal to 0, on 1 x is equal to 1, on 2 x is equal to 1, on 3 x is equal to 1. Now the thing that varies here in this finite state machine is the transition. If I have to move from off to on 1, I have to make sure B is high and clock is also high. So I am putting B and clock together. It should be equal to 1. And in case if B is not high, so if it is something we show it by complement, B is low, then if the positive edge of the clock comes, we will stay in the same off state. This is what happens here. I am starting with off. I am first looking for the value of B. It is 0 in terms of variables is B complement. So even if positive edge comes, I will still stay in the off state. Then again here B complement off, B complement off. Only at this instant it goes high, I move to on 1. And once I reach on 1, thereafter I don't need to care about the input B. So clock comes, I will move to on 2. Clock comes, I will move to on 3. Another clock comes, I will move to off state. Right? So these are 3 examples that we have considered here just to put forward the concept of finite state machines. And if I have to summarize in a general way what we have learned from these 3 examples is that if you mathematically, formulate this, it actually tells us, let's summarize it, that with respect to finite state machine, because understanding FSM is very important. You will see later on that FSM is the first step in the design methodology that we use for designing sequential circuits. To summarize, an FSM will always have a set of states. This is a primary requirement. For example, in the first example, we had 2 states, off, on. Second example, we had 4 states, off, on 1, on 2, on 3. Third example, again, we had 4 states, off, on 1, on 2, on 3. So whenever you talk about FSM, one thing is mandatory, that it will always have a set of states, and they will be finite in number. A set of finite states. This is the first, first property of an FSM. Then second, it will have a set of inputs which is optional. Like in the first 2 examples, we didn't have any external input. We only had the clock. But in the third example, we had an input B. So set of inputs is optional. It may be or may not be there. It will have a set of outputs. Like in the 3 examples, we had X as the output. You can have many more. Fine. So this is another property of a finite state machine. Then there will always be an initial state. Like in all the 3 examples that we considered, we had off state as the initial state. So this is basically the state uh, from which where we start, because every time you power up a system, it has to start from somewhere. So we need to have an initial state in an FSM. And I told you that we typically use this kind of arrow to indicate what our initial state is. Fine, you can just have a look here. This is my initial state. Fine. So a set of states, a set of inputs optional, and a set of outputs, then it will always have an initial state. Fine. Then it will have a description of the next state to go to based on the current state and the values of inputs, if any, if there are inputs. Fine. So this means a finite state machine should also have this information that currently if I'm in a particular state, how I can move from this state to the next state. Fine. Now in the examples, we use directed edges. We use directed edges with associated input clock conditions. In the first two examples, we had only clock. In the third example, for the first transition, for the transition from off to on one state, we had clock and an external input B. Fine. And normally we don't show clock in an FSM. Like I showed it here. But like I said, a state is the concept that is based on timing, and the source of timing in a sequential circuit is clock. So it's always implied that clock will always be there. Fine. So we don't explicitly show clock as a transition on the edges. So we will be using finite state machines of this nature. If I redraw it for the last third example, we'll have a set of states of on 1, on 2, on 3. Then we'll define the output for each state. And initial state. Then as I define the transition, I will only mention on these edges, which actually show the transition, I will only mention the inputs. For example, this happens for B, this happens for B complement. I don't write clock here, I don't write clock here, I don't write here, because it is implied that for every transition, clock needs to get high. If there is some external input, then you have to show it as a part of FSM. So this is the convention we'll be using. Fine. And then you should also have a description of what the output in a particular state is. Like in this example, off state output is 0. Similarly for on 1, on 2, on 3, the output is 1. So this is the basic finite state machine. Fine. As we learn the methodology of designing sequential circuits, then as we take practical examples of design, this will get more clear. But I needed to give some brief introduction about what a finite state machine is. And these are the constituents of the finite state machine. Fine. So in the next video, we'll actually look at the methodology which we use to implement this FSM, which indirectly will implement our sequential circuit. So I'll stop here.